Concept called a sampling distribution. First thing I'm gonna do is run the setup so I can have access to my data set, and I might need the library Mosaic and NHANES. So a sampling distribution is how a sample statistic is distributed when repeated samples of size n are taken. This seems a little complicated, so let's go through an example of what this actually means. So as my example, we're going to have the temperature of a healthy person is considered to be 98.6 degrees Fahrenheit. Is that really the case? Consider a sample of 60 healthy people's temperatures. So here we've got a sample. This is the sample of those temperatures. Actually, there's only 59, but that's okay. We're close enough. And so we're going to run this density plot. So you use a density plot to see if the sample is from a population that's normally distributed. You want that density plot to be bell-shaped. We're also going to do a normal quantile plot with this GF underscore QQ, get you a density plot. Everything's the same thing. And you want that I'm sorry, not density plot, a normal quantile plot. And that normal quantile plot, you want to look linear. So let's go ahead and run that. I'm looking at my density plot. That does look like a nice bell-shaped curve. I'm looking at my normal quantile plot, and it does look somewhat linear. That looks like there's a little bit of an outlier, but overall, it looks fairly linear. So it looks like this sample is from a population that is normally distributed. This sample has a mean of 98.2 and a standard deviation of about 0.76. We're going to pretend that this is actually our population. And then we're going to work with that just to help us understand this. So suppose you take a random sample of 10 temperatures from those 60 healthy adults. Let me go ahead and run this. Oh shoot. There we go. We're now going to run it. Sorry, I had a low error. So we ran this. We can't see all of it, so let's open it up so we can see all the decimal places. So 97.2, 98, so forth, all the way down to 98.4. That's our sample. I'm going to run this again and kind of see what happens when I run it again. And when I run it again, I go back and look at this, notice those numbers have changed. And that is because we happen to have a random sample. So we're taking a sample from this, so the values should in fact change. All right, let's go ahead and find the mean of these sample values. So the mean from this sample. The mean from this sample looks to be 98 point something. And so instead of just doing this one time now, we've done it once, we've calculated this, we found the sample mean. We're going to repeat this process, let's say 100 times. And each time we're going to calculate the sample mean. So we're going to actually we're going to call it trials to save them somewhere. So we're going to save these sample means somewhere. We're going to do this 100 times. We're going to use our temperature data set. We're going to take a sample of size 10 from it, and then we're going to calculate those means from every single one of those. And that's what's going to go into these trials is those sample means. And then we're going to do a density plot and calculate the means from those. So I'm going to go ahead and open up trials so you can see what it looks like. So what this is the first time I ran it at sample size 10, I got a mean of 98.23. The next time I did it, I got a mean of 98.64 and so forth. I can see each one of these values is a different mean, sample mean from that sample of size 10. Notice I did this 100 times. So we did this 100 times. Each one of these values, again, is a sample mean, no longer a data value itself. They're just sample means. And if I look at this, it looks somewhat bell-shaped. Okay, so it looks like it might actually be somewhat like a normal distribution. If I did this again, probably get something different looking. Looking at this, I notice my sample mean is 98.2 and my standard deviation is about 0.23. So it does look like it's a normal distribution. It looks like the sample mean is 98.2, which is almost the same as the population mean. If you go back up to our population, remember our population mean was 98.2. So we're almost the same. The standard deviation noticed before was 0.76. My standard deviation now is 0.23. So it's not exactly the same. 0.76, 0.23, that's about a third of the population standard deviation is at 0.23. We'll come back to that in a little bit. Now we want to know, what does this distribution look like if instead of taking a sample of size 10, we take a sample of size 30. So this, so let's run this one. So we're going to go ahead and run this idea. We're going to do this again 100 times. We're going to take a temperature. We're going to do 30 times, and we're going to calculate the sample means from each one of those samples we take. And then we drop the graph. And look at this graph again. Looks somewhat like a normal distribution. Notice here the mean is 98.2, which is basically the same mean as we got here, was 98.2. And it's the same as our population mean of 98.2. Notice the standard deviations are much, much smaller. So now let's do another example. So now let's do another example of this kind of same idea. And so now we're going to run the same thing again, but we're going to do for a different variable. And this is actually from the NHANES data set. It's the smoke age. That's the age that somebody actually started to smoke. And we're going to again look at what that distribution looks like at the start. And looking at this does not look like a normal distribution. It's definitely skewed to the right. It has some peaks, extra peaks going on here. Definitely is not. The mean is 17.8. Standard deviation is 5.3. Now let's take the 100 samples of size 50 individuals from this data set. So we're going to do the exact same thing we did before. We're going to take this again. Again, the population mean is 78.6, and the standard population standard deviation is 5.36. So let's run this one. So notice that this sample, remember we took samples of size 50, and then we calculated those means. So this is the means, these sample means, and notice that shape looks kind of almost like a bell-shaped curve. Let's look at the standard deviation and the mean. The mean is that's still 17.8. So it looks like the sample mean stays the same. The standard deviation is again much smaller. It was 5.3, now it's 1.2. So looking at this, we can see that this mean, and we can call this the mean of the sample means. The symbol for this is mu with an X bar. That means it's the mean of those sample means. I calculated those sample means, then I calculated the mean of the sample means, and that's 17.8 years. And the standard deviation looks like it's 1.25. And again, this is the standard deviation of those sample means. So this is the symbol we use for it, but it really is just thought of as the standard deviation of the sample means. The mean of the sample mean is almost exactly the same as the mean of the original population. Standard deviation is smaller though. So let's see, why is it smaller and how much smaller it is. And we also want to see, why did we have a distribution that did not look normal, but these sample means now look somewhat like a normal distribution. So that's what we want to talk about next, is how come the sampling distribution of the sample means appears to be normally distributed when the sample was large. This is known because of a theorem known as the Central Limit Theorem. The Central Limit Theorem says if the variable has any distribution with a mean of mu and a standard deviation of sigma, as the sample size n increases, the sample mean, x bar, becomes more distributed as a normal distribution. In other words, as your sample size gets larger and larger and larger, and you keep taking sample means of those those sample means become normally distributed. Also notice the mean of the sample means is the exact same as the mean of the original population. We saw that in both examples. We did notice the standard deviations of those sample means got smaller, and it actually gets smaller by a factor of the square root of n. So that's why it's a sigma divided by the square root of n. It gets smaller by that. We're getting rid of those extreme values, so we don't have those extreme values and things get smaller. The z-score for this would be normally it's z is equal to x minus mu over sigma, or x minus the mean over the standard deviation. But here we're dealing with x bar, so it's x bar minus the mean of x bar over the standard deviation of x bar. But since we just found out the mean of x bar is just the same as the mean, standard deviation of x bar we found out was the standard deviation of the square root of n. So we get this little bit new formula for this. Now the question is, how big does n have to be? Well, that depends on the size of n, and it also depends on the shape of the original distribution. So it actually depends on the how the variable is distributed. If the variable is normally distributed, then the size of the size of n can be anything over 2. You have to have a 2 because you need a sample. Or even 2 or more. If the variable is not normally distributed, then the sample size of n is 30 or more, especially if if standard deviation is mound shaped. This is just a standard we're using. 30 isn't like a hard and fast rule, but 30 seems to work. We actually saw with this one, we had a sample size of 50 and we got a nice normal distribution. I wonder if we changed our sample size to 30, what it would look like. Let's just do that and see. And it doesn't look perfect. So again, that 30 is just kind of an approximation, just kind of a standard we use. It's not too bad, but it wasn't perfect. All right, so let's do another example. Let's finding probabilities of the sample mean. Let's do an example. A variable is not normally distributed, but is mound shaped. It has a mean of 14 and a standard deviation of 3. If you take a sample of size 10, can you say that the shape of the sampling distribution what the sample mean is? And we can't say what it is because we just talked about that you have to have, if it's not normally distributed, then you have to have the sample size of 30 or more. And this is only a sample size of 10. So there's nothing you can say. Since the sample size is less than 30 and the original random variable, and the random variable is not normal. We can still calculate some things. So find a sample of size 10, state the mean and the sample mean of the standard deviation and the standard deviation of the sample mean. So let's go ahead and look at that. So the mean of the sample mean, again, you can use a symbol, but it's the same as your original mean. So it's the same as the mean, which is 14. The standard deviation of the sample mean is the standard deviation, which we found to be 3, over the square root of your sample size. So our sample size is 10. Notice I wrote SQRT for square root. That actually is a way a lot of computers do square roots. I'm not going to care what this number actually is, so I'm just going to write it as being this. I don't need to know what that number is. Now let's say you take a sample of size 35. What can you say about the shape of the distribution of the sample mean? Well, in this case, because the sample size is over 30, then you can say the sample mean will be normally distributed. And that's because we have a sample size over 30. For the sample size of size 35, what is the mean of the sample mean and what is the standard deviation of the sample mean? Well, the mean of the sample mean is the same as the mean of the original data. So it's still 14. That didn't change. The standard deviation of the sample mean is again the standard deviation of the original variable, which was 3, over the square root of my sample size. In this case, my sample size was 35. This one will be smaller. We get less variability when you get a bigger sample. One more example, according to the WHO Monica project, the mean blood pressure for people in China is 128 millimeters per mercury with a standard deviation of 23 millimeters per mercury. Blood pressure is normally distributed. So the first question is, state the random variable. So the random variable, what we measured is blood pressure. Then we want to know, suppose a sample of size 15 is taken, find the shape of the distribution of the sample mean. Well, since blood pressure is normally distributed, I don't care what the size of the sample is, so I can say that the sample mean is normally distributed since the original variable, since blood pressure is normally distributed. So since the original random variable was normally distributed, the sample mean will be. I don't care what the size of the sample is. Again, I'd like to find the mean of the sample mean. Well, that's the same as the mean of the original data. The original data mean was 128, so that's still 128 millimeters per mercury. If a sample size of size 15 is taken, state the standard deviation of the sample mean. Well, again, that's the original standard deviation, which was 23, divided by the square root of my sample size, which in this case is 15. Suppose a sample of size 15 is taken, find the probability that a sample mean blood pressure is more than 135. So we're looking for the probability that the mean, the sample mean, is greater than 135. Well, we will do this using an R chunk. So we're using a normal distribution because we can assume it's normally distributed. If I didn't know that it was normally distributed from up here, if I didn't know this value, then I couldn't be doing this. But since I know this, I can still use my P norm. My value I'm looking for is 135. My mean is 128. We just did that up here. And my standard deviation is at 23 over the square root of 15. And then I want to have lower dot tail false, because again, we're going to be greater than, so we're saying we're in the upper tail, not in the lower tail. And there is my my probability. Would it be unusual to find a sample mean of 15 people in China of more than 135? No, because this is not greater than 5%, so not unusual. Since the probability of the sample mean being greater than 135 is greater than 5%. So if you did find a sample mean of 15 people in China to be more than 135, what would you conclude? Nothing. It doesn't seem unusual. Okay.